I'm Jim Lazar. I am one of the creators of what we're calling the Electricity Brain Trust. It was created by myself and Ahmed Faruqi. It evolved out of a email string that quickly grew from 6 participants to 306 participants, at which point it became totally unmanageable. And we converted that list into a Google group. It's nothing more than a Google group. And this is the first event that the Electricity Brain Trust has convened. It's being convened on my personal Zoom account. We're limited to 100 participants. We're at 23 now. I would be frankly astounded if my limit proved to be a constraint. I'm going to give just a couple of Zoom basics, then go through and methodically mute anyone who isn't, and turn it over to Adam Corr. Zoom, most of you have probably used extensively. There are a couple of things. If you take your cursor to the lower left of the corner of the screen, you get the mute button and the stop video button. If you open the participants list, there is a raise hand function, which I will try to keep an eye on as we get into questions. There is a chat function. I may do a less good job of keeping an eye on that because I'll be looking at the raise hand function. And Ahmed is, I think, unable to join us. He thought he was going to have it and then had this hour taken away from him by some paying client. He's still working. I retired from RAP in June and have a little more flexible schedule. This forum evolved quite quickly from a discussion on the forum, about a dozen or so participants discussing the new RethinkX report on rethinking electricity, rethinking energy. We decided to schedule the forum, and I sent a note to Tony Seba, and he lateraled it to Adam Corr, his co-author or lead author, and we're thrilled to have Adam with us. And unless there's something really urgent, I'm just going to hand it over to Adam, let him introduce himself and get into a short presentation and then a discussion. I do plan to end this promptly an hour from when it started. So Adam, you can unmute yourself and take it away.
Hey.
And I'm going to go in and mute people who aren't muted.
I hope everybody can hear me.
Good.
Okay, so well, let me introduce myself and RethinkX very quickly first. I'm Adam Dorr. I'm a research fellow at RethinkX, which is a think tank that was founded by Tony Seba and Jamie Arbib. And many of you may be familiar with Tony's work. His focus in over the last decade or more has been on clean disruption. He's literally written the book on that. And I've been working with Tony for just over 3 years now. Our core expertise is on technological change and technology disruption. That's the focus of what RethinkX does. That's what we analyze, what we try to understand, and to the extent that's possible, what we hopefully anticipate and forecast with reasonable accuracy and value. So I want to preface all of this by saying that every single one of you is almost certain to be a more knowledgeable and greater expert than I am when it comes to electricity. But our core focus, research focus at RethinkX is bringing a clear technological disruption theoretical framework to bear on a variety of different industries and sectors. So we now have done 3 of what are quite foundational sectors of the global economy: transportation, food and agriculture, and now energy, which builds on Tony's earlier work. And so what we're trying to do at RethinkX is understand not just the implications and the choices that are before us over the next decade or so from the disruption of electric power as a sector itself, but rather how disruptions across multiple sectors throughout the global economy are going to occur and interact and catalyze one another over the next decade. And so that's really what this is, what our work is all about. Very quickly, my background is in environmental science, master's degree, University of Michigan, with a focus on the sustainability of complex systems, and then a PhD at UCLA, understanding the environmental policy and planning around technological disruption. So at the Luskin School there. So without any more details, I'm more than happy to answer questions about Rethink X and the work that we do in general afterwards, if that's what folks are interested. But I'll just dive into my slides. I've got about 10 minutes worth, and then I'm happy to stay around as long as anybody's available until my next call, which is 2 hours from now. So I'm happy to stick around. Okay, so the title of our report is Rethinking Energy 2020 to 2030. 100% solar, wind, and batteries is just the beginning. And what we aimed to do with this specific report was to answer the question: is it possible to have an electricity system comprised exclusively of these three technologies, of solar, photovoltaics, of onshore wind power, and of lithium-ion battery storage? That was our organizing research question that we are trying to answer. And the context for asking that question, and then the larger picture of our findings emerging out of this are that we expect these three technologies to drive a fundamental disruption, perhaps the most profound disruption of the energy sector worldwide in over a century. And I'll get into the reasons why, and then talk about what we see as the implications, and then very quickly talk about perhaps some of the choices that we have to face as a result of this. So, like other technology disruptions, this one is the result of a convergence of three rapidly improving technologies that have now reached the point where their capabilities allow them to offer an economically competitive alternative to the incumbent technologies we've used for many decades now. So it's costs that are driving this disruption, and it means that incumbents cannot compete now. And we are 10 years ago, this seemed implausible, but now we're daily seeing issues, reporting in the news about solar in particular, and also wind being the least expensive forms of electricity generation in history. So this was theoretical in Tony's work when he was beginning his work a decade or more ago, and he's frankly, many people thought he was completely crazy. But having the right theoretical framework for understanding the dynamics driving what's going on has allowed him, and now Rethink X, to make some good predictions about where costs are headed, how far they've come and where they're headed. And this is the writing on the wall, that incumbents simply cannot compete going forward. Okay, so what we think is going to happen is that disruption is inevitable, but that doesn't mean it's inevitable everywhere by 2030. What it means is that and what we mean in our report is that it is possible by 2030 in areas, in regions that choose to lead the disruption. So although disruption is inevitable, broadly speaking, over time, when we say 2030, we mean that it's possible by 2030 in some regions, contingent upon the choices that society makes. And one of the other most important implications, high-level ones here, is that disruptions don't just witness the rise of a new technology, they wipe out the incumbent technologies that they're competing with and ultimately replacing. And what that means is that even starting now, because this disruption is now underway, coal, gas, nuclear, and other conventional power generating assets are going to be stranded by this disruption. And of course, this is crucial. So let me go through very quickly and talk about some of the dynamics and how we understand them, and then I'll share with you the findings in our research, and we can talk about them. So again, cost is what's driving this. And I'm sure as you're all familiar, the cost improvements over the last decade since 2010 have been absolutely spectacular. We've got an 82% decrease in solar PV since 2020. We are predicting another 72% decline, and I'll explain what our logic is in a moment. But you can see on a logarithmic plot, which is how we work with our data internally, the improvements have been remarkably consistent, as long as you view them on the appropriate logarithmic scale. And we are extrapolating this same trend that's been consistent for a decade or more now forward through until 2030. And so over the last 10 years, we've had remarkable improvements, and we expect those improvements to continue. And I'll explain why we expect that shortly. The same goes for wind. It's not quite as spectacular, but there have been remarkable improvements. The cost of onshore wind power has fallen by almost half in the last decade, and we expect it to fall further in the 2020s. So that in a 20-year period, in a 2-decade period between 2010 and 2020, wind will have fallen by a factor of 3 in its cost. And again, we are extrapolating forward from the present through till 2030, based on the trajectory that we've seen. So this is an extrapolation of well-established historical trends. Batteries are even more spectacular. They're truly show-stopping trend of the last decade has been in batteries. And it's almost 90% decrease in cost since 2010. We're expecting 80% more during the 2020s for a total improvement in this 2-decade period of 45x. It's just stunning amount of improvement. So why do we expect that that level of cost improvement? Because what we often get as pushback is, well, we're going to hit a floor any day now, right? And forgetting that that same argument has been leveled at all 3 of these technologies for more than a decade. Oh, it's, next year is when we're going to hit the price floor, the cost floor. And so I'll explain quickly why we don't think that's the case. The main reason why is that disruptions historically, they always follow an S-curve. And the first phase of the disruption S-curve is exponential, as I'm sure is familiar to many of you. Incumbent or conventional forecasts tend to make linear projections. They tend to not assume that these markets are growing exponentially, or that they can continue to grow exponentially. And that's the fundamental flaw. So far globally, and it's the global trends that matter, not the local ones. The global trends for all 3 of these technologies have been exponential. Solar adoption is clearly exponential. Wind adoption has been exponential. It may be leveling off, but it's too early to tell whether we've reached the inflection point for wind yet or not. And batteries, of course, are still growing exponentially and are very likely to continue doing that. So what makes RethinkX believe that these trends are going to continue, that the exponential growth is likely to continue through the 2020s? The reason why we expect that is because of causal feedback loops. So for any new technology, lower costs drive more demand. That drives production investment. Supply expands and lowers costs further. So this is a feedback loop. And it's not the only one that's at play. Other important ones are that more demand drives additional infrastructure investment, additional government support. Those also expand supply. As supply expands, the underlying technologies tend to improve, so you get better capabilities. The public becomes more accepting of the technology. We're certainly seeing this now with renewable energy. And you get stronger network effects arise around major brands and platforms. So as demand grows for the new, it erodes the demand for the old technology. So you get precisely the opposite happening for the old technology. You get a decrease in revenue, supply contracts, loss of economies of scale result in higher costs, which translate into higher prices, and demand shrinks. And when that happens, you have less profit, you have a contraction of production investment and infrastructure investment, and you have a reduction in government support. All of which serve to constrict supply further. And at the same time, the public tends to become less accepting of any of the technology's flaws. So again, we're certainly seeing this with fossil fuels right now. And the network effects tend to erode, all of which reduce demand even further. And as demand for the old declines, that in itself feeds back into driving demand for the new technology. So this is a very simplified version of some of the causal feedback loops that are at work, that are driving the disruption S-curve. And this is why it's just a fundamental error to make linear forecasts when a technology disruption is imminent. History simply does not bear out any examples where we have a long, slow, steady, incremental, linear transition from an old technology to a new technology. Please, if anybody has ever found an example of those, please send it to us. We're looking for counter examples so that we can understand them if they arise. We've never found one, but there are literally hundreds of examples of technologies that follow a clear sigmoidal, an S-curve. Okay, so this is why we fully anticipate that there will be a disruption S-curve for these three technologies. Okay, so how long is that exponential phase going to last? Well, again, we look to history. We look to the empirical evidence for other disruptions. And what we see is that the inflection point for when the disruption curve, the exponential trend inflects into its final sigmoidal form and growth begins to level off, that tends to happen when about 75%, there's a fairly large range. The standard deviation is at least 10%, but on average, it tends to occur at about 75% of the market size. So what we should expect is that the final market size, wherever this is growing to, that we will grow exponentially until we reach about 75% of that. So here's the final lesson. And this is all based on the SIBA technology disruption framework. So this is Tony SIBA's theoretical framework that he developed. Final thing to understand is that disruptions almost always result in a much larger market, much larger new system. So the new systems that are produced by technologies and that are the consequence of technology disruptions almost always result in an end market that is significantly larger than the one it's replacing. And the range of difference is enormous. So take a couple of historical examples. It's the automobile, right? When the automobile disrupted horse-drawn transportation, you didn't just replace every horse with one automobile. There are so many more uses for automobiles, and they facilitate so much more productive activity throughout the economy in different ways, that the new system of transportation that resulted from the automobile disruption of horse-drawn vehicles, the final market for automobiles was vastly larger, an order of magnitude at least larger than the market for horses. And you can run through other examples that are similar to that. A truly spectacular one is the difference between digital photography and film photography. So if you just measure on the key metric, which is the number of images generated or captured or consumed, we're at maybe 3-4 orders of magnitude, perhaps more. Digital images are being consumed than celluloid images were being consumed 25 years ago. So the new system tends to be much, much larger than the old one. And we think that this is almost certainly going to be the case for the energy disruption as well. So putting all those pieces together, this is why we think that the exponential growth is likely to continue through the 2020s, and that costs are therefore going to be continuously driven down the existing experience curves, and that those trajectories that we've seen so far on the logarithmic plots are likely to continue all the way through until 2030 before they begin leveling off. Okay. So conventional forecasts obviously get this wrong. These are annual International Energy Agency World Outlook forecasts, and they make a linear projection every year and then adjust it. So this is just an example of conventional forecasting and the consistent errors that are made there. And it isn't just a failure to forecast the new technology. The old technologies are often forecast poorly as well with similar mistakes. So this is the Energy Information Administration's forecasts for coal. Obviously, they've been forecasting mostly with wishful thinking here, either a linear continuation of the existing status quo or even some recovery. but coal in the United States has already been disrupted by fracking. Fracking for natural gas is what disrupted coal. And that we're now transitioning from the fracking disruption into the solar and wind disruption of coal in the United States. So you can see that these trends are pretty clear. Okay, so that's the basis of the theoretical basis for our disruption analysis of energy. And so what we did in this research, this report we just put out, was we looked at 3 regional case studies. And we asked, okay, is it possible? This is the first thing that we asked: is it possible to have a 100% solar, wind, and batteries electricity system? There is a prevailing narrative that says this is simply not possible. It's either physically possible, or at the very least, it's economically impractical. It's not feasible economically. So we looked at 3 different geographically representative cases in the United States. And what we did was we took the actual solar and wind generation in those regions as reported by their the ISOs there, the systems operators. And we normalized the data and adjusted for capacity additions over the course of a 2-year period, because we have 2 years of very high quality, high resolution, so hourly data for each of these 3 regions. This was the only period where these data were available and reliable, very high quality data. And what we did is, after normalizing those the solar and wind data, we were able to then model, and we used Stella as our systems dynamics modeling environment. We were able to model the battery requirement such that the system has 0 faults in that 2-year period. In other words, that we were able to determine exactly how much battery capacity is required to go along with the solar and wind resources that are available in each of these 3 regions. And so by normalizing the solar and wind data from existing generation, we're able to have a proxy indicator of the sunshine and the wind resources that are available in those regions. We do not simulate solar resources or simulate wind resources. Those, I don't mean to denigrate those approaches. Those are certainly valid approaches, but simulation, as I'm sure we all know, has its own downfalls, has its own shortcomings. Because obviously you're making many assumptions, and there's the possibility of incorporating an awful lot of error from a variety of endogenous and exogenous variables. Our approach bypasses a lot of that by simply taking the generation that has occurred in these regions and using that as a direct proxy for the sunshine and wind that were available and were captured and were utilized by these technologies over a 2-year period. So that's why we chose to this approach. What we did was we ran—
I'm going to interrupt you for just a second here.
Sure.
Ahmed Faruqi, my co-conspirator in creating the Electricity Brain Trust, has been able to join us for a few minutes, and he's going to have to leave again soon. And I just wanted to give him 60 seconds to say hi and welcome to folks before he has to go.
Thank you very much, Jim. Yes, it's a pleasure to be here, and I wish I could stay for the whole hour. I am going to watch the recording, which we are making here. And Adam, you're certainly laying out some very intriguing scenarios here. I would be interested in seeing what the final results are, but I'll leave you with one question. And that one question is, suppose you had done what you're doing now 20 years ago, looking at historical trends, looking at S-curves, looking at cost reductions and so on. Would you have predicted what's happening in 2020, 20 years ago with your approach? And if you would have predicted it, how would you have done it? Would you have used the same tools? Would you have talked with experts? Would you have looked at alternative scenarios? Or would you have been able to, with a crystal ball, tell us where we are today?
So Adam, you can take that as the first question when you're done, and go ahead and pick up where you left off.
Well, I'll finish my slides, but please don't let me forget to answer that question when I get to the end. It's a very good one, and it's a very interesting one as well. Yeah, very, very interesting one. Well, so let me just back up very quickly and say again that what I'm showing in this slide here is sort of a visual representation of the sort of output of our modeling. And what we did was we ran hundreds of thousands of scenarios. We looked at different combinations of solar capacity, wind capacity, and battery capacity. And we modeled all of them with looking at the dimension of cost. And so the result was a large series of heat maps that lets us see and each of these, we modeled all of these iterations over time, looking at how costs change over time. And what we found is that, and this in itself isn't surprising, what we found is that there are many different, thousands of different combinations of solar, wind, and batteries that could physically provide 100% of our current electricity demand. And so that in itself isn't surprising. But what was interesting was we discovered an underlying dynamic for the balance, the way that the costs are distributed in this space of possible solar, wind, and batteries systems. So very briefly, it's really just a balancing act. You can either have a relatively small amount of solar and wind generation capacity, and then backstop that capacity with a very large amount of battery energy storage capacity to get you through the most challenging periods of the year. Typically, the shorter days of winter that are also cloudy. Those are tend to be the most challenging times. So that's one option. The other option is, of course, the reverse, to have a much higher amount of solar and wind generating capacity so that even on short, cloudy winter days, you can still generate a fair amount of electricity, and then that lowers the battery requirement for the system. So it is a balancing act. There's a trade-off. And what we discovered is sort of what that trade-off looks like, what it's characterized by. So when we plot viable systems, these are all viable systems, 100% solar, wind, and battery systems of various combinations of solar, wind, and battery capacity. When we plot these, when we plot cost against the generating capacity, just the generating capacity, what we find is that it produces a very interesting convex cost function, a U-shaped curve. And we call this the clean energy U-curve. We are not the first to produce this result, but I think we are the first to identify its significance. You can see versions that look a little bit like this of data that have been published by others, but nobody seems to have really fully grasped the significance of this. And I should also mention that if I could zoom out on this graph, the U-curve would shoot off up into the stratosphere as you move further away from the minima. And so if you were to get to 1.5 or 2x generation capacity on the left-hand side, the curve would just be up off the top of your screen and out through the roof of your house. And that if your thinking is limited to that window of what's possible, then things are going to seem very expensive, which of course has been a predominant part of the conventional narrative up until very recently. But I think this is a very useful tool for understanding how to optimize a 100% solar, wind, and batteries configuration on the basis of cost. And it's not obvious. This is non-obvious, and it has some very significant implications. So let me add some detail here. I already mentioned that on the one hand, you can have a system that will be expensive because it's dominated by batteries and has relatively little solar or wind generating capacity. You can have the reverse. You can have much smaller battery capacity, much larger generating capacity. And what you're really looking for is some sort of optimal combination in the middle, right? And so the least expensive combination is represented by the bottom of the curve. This is sort of a sweet spot between balancing battery cost and solar and wind cost. This is what the U-curve shows us. What's so unintuitive, what's so counterintuitive about this is where that sweet spot is located. And we have it positioned here approximately because this is an idealized version of the curve. For our three cases, for California, Texas, and New England, we found that the sweet spot occurs between 3x and 5x of the existing generating capacity. So in other words, the sweet spot, the cheapest, the least expensive solar, wind, and battery system will have somewhere between 3 and 5 times the generating capacity of today's electricity system, today's grid. So whatever the peak generating capacity of is in California today, the cheapest solar, wind, and battery system will have 3 to 5 times that much. And this is very unintuitive. This is very unintuitive. If most of the research of the last 10 years, and things are changing in the last 2 or 3 years, but for most of the last decade, the idea that it would be cheapest to build that much generating capacity it would have seemed absurd. Simply didn't seem plausible to build more than say 2.1, 2.2 times generating capacity. And then of course, with that amount of generating capacity, you need a very large quantity of batteries. Now, because all of this is non-linear, none of this is linear, we have a very surprising second finding, which is that when you're at that optimal point, you only need 35 to 90 hours worth of battery storage. Again, this is between our three case studies, California, Texas, and New England. New England needs about 87 hours worth of batteries. California needs about 37 hours worth of batteries, much sunnier there. But this is far, far less battery energy storage required than is widely believed. So even in industry, even in academia, the idea that we could have a viable system with that little battery energy storage is not widely known. And the idea that is where the cheapest combination lies, I think this is also quite a surprising finding. So the clean energy U-curve is a very useful tool, I think. We actually already have groups around the world reaching out to us with interest in applying this tool to their own systems. So this isn't a pretty extraordinary finding. It's got some great implications for future analysis. We hope that others will take this and run with it. Very quickly, we put some numbers on our findings. Of course, these are based on assumptions. We have a very highly constrained analysis that produces these numbers. And others, our goal as a think tank is to reframe the conversation and then allow others to keep pushing the ball down the field. So what we found with our analysis is that the generation and storage assets, the solar, wind, and the batteries, the generation and storage assets themselves, this is what they would cost in the 3 different regions. Not cheap, but not astronomically large either. Extrapolating to the whole country, the assets themselves would cost less than $2 trillion. Right? So over 10 years, that's 200 billion a year or less. That's less than 1% of GDP. I mean, again, this appears to be substantially more affordable than is widely believed. Okay, so I want to very quickly get through some of the constraining assumptions and then talk about superpower very quickly before ending. So constraining assumptions. Our analysis is very, very tightly constrained. We wanted to establish what was possible in the limit for solar, wind, and batteries systems, 100% solar, wind, and battery systems. So our analysis has no electricity imports. You can't cheat by importing electricity from a neighboring region that's got clear skies. No distributed energy generation or storage, right? No rooftop solar, no power, Tesla power walls in your garage, none of that. This is a grid scale only analysis. No electric vehicles. So no changes in demand from electric vehicles, and the electric vehicle disruption is an entirely separate thing that we have written about, and no battery energy storage capacity from those electric vehicles. No energy arbitrage, that's buying low to sell high later. No peak shaving or shifting demand to avoid peaking requirements. No conventional legacy power plants providing emergency reserve. No technological breakthroughs. So, and this is standard for all of our analyses. We only extrapolate forward based on technologies that have an established cost history. But these are certain to come in the 2020s. Perovskite solar photovoltaics and solid state lithium ion batteries and a number of other potential breakthroughs are in the works, and we're likely to see at least some of those during the 2020s. And then very importantly, we assume no subsidies, no carbon taxes, and then finally, no infrastructure changes. So our analysis does not include what it would cost for interconnection, and then any changes in the infrastructure that would be required for transmission and distribution. And I can explain details why we made that assumption if anybody's got questions. But all of these factors vary enormously from one region to another, enormously. And so any specific analysis for a local region that's intended to be a forecast would need to try to model all of these variables. Now, one thing you may notice is that most of these are conservative. They're not merely constraining, they're conservative. If you were to account for these, most of these would accelerate the disruption, not slow it down. That's very important to keep in mind. The bar is probably not so high as our analysis suggests because of all of these other factors, which could each serve to accelerate the disruption. Okay, very quickly, let me talk about superpower. Superpower is what we call overproduction. So, and again, we have given it a different name because the term overproduction is so misleading and embeds assumptions about the energy system and its future that are not valid. So when we build a 100% solar, wind, and battery system, we obviously have to build it so that it's capable of meeting our needs in the most challenging periods of the year, those short, cloudy days of winter. But of course, the corollary of that is that for the rest of the year, for the vast majority of the rest of the year, you're going to have excess, you're going to have a surplus electricity generating capacity. And the electricity that's generated, and this is extremely important, the electricity that's generated will be predominantly by solar, the surplus. And because of that, it will have a marginal cost of near zero. So when the sun is shining, solar panels just make electricity quite happily. There's no fuel, there's minimal additional wear and tear. The distinction between when solar panels are generating and when they're not generating, the cost premium, in other words, the marginal cost on each additional unit of so kilowatt hour of energy is minimal with solar photovoltaics. It's an extraordinary quality. Wind power, to some degree, but a lesser degree. You still have significant wear on wind turbines if they're producing electricity. But for solar panels, for solar PV specifically, the marginal cost is very close to zero. And so you have this extraordinary property, which is that a 100% solar, wind, and battery system will have the ability to produce a very large amount of surplus power, which we call superpower, at almost zero marginal cost. And this is really, really an unintuitive feature of the system. And it isn't just once in a while. So depending on the amount of sunshine that's available, in sunny places, you're going to have some superpower on most days. So in California and Texas, 93% of days in the 2-year period that we analyzed would have had some hours of superpower production. Even in New England, which is not got anywhere like the solar resources or anywhere like the wind resources of Texas, you still have superpower on 64% of all days. So we're talking about an enormous amount of additional electricity from a 100% solar, wind, and battery system. Now, there are a wide variety of ways that we can imagine that that this additional electricity could be put to use. And there, these images here are simply intended to evoke some of those possible uses. But I want to emphasize that it's extremely difficult in any disruption to predict specifically what the uses are going to be. So I'll give you an example. In 1995, it was possible to anticipate that the internet was going to be extremely disruptive to a large number of industries because of its potential to lower the cost of communication and information to near zero, to slash the marginal cost. So prior to that, we all remember long distance phone calls where you had to pay by the minute. In the early days of the internet, we remember dial-up that you had to pay for by the minute. Very quickly, the internet reduced the cost of communications, as we see with the Zoom call, to nearly zero. And so it was very difficult then to predict what specific business models, what specific lines of investment, what specific, let alone what specific companies would be successful going forward. And it might have been tempting to say, well, nobody can make any money with zero margin or near zero marginal cost communications and information. And yet it's funny, almost precisely the opposite of that happened. The 5 largest companies in the world are companies that made their fortune thanks to the internet: Amazon, Google, Microsoft, Apple, and Facebook. Right? Total market value right now is about $5 trillion. So obviously people have found a way to make a lot of money, to realize a lot of value with successful business models, despite a complete transformation in where the value is embedded in the system. So we are thinking that something very similar is going to happen to energy, that the world of bits, as it was transformed by the technology that slashed marginal costs to near zero. We are imagining that something analogous is going to happen in energy as a result of superpower. So this is a very exciting thing to think about. It's also very different than the way overproduction is conceived of today. Today it's conceived of as a problem. And what's the response to overproduction today? Curtailment, right? But fundamentally, flushing gigawatt hours of clean, nearly costless energy down the drain with curtailment is completely irrational. Frankly, it's insanity. That's not any kind of solution at all. I think what we're likely to see instead are a wide variety of what seem today quite radical new business models emerging to take advantage of this extraordinary opportunity. And it's really no coincidence that the incumbent system views these new behaviors as problems and not as opportunities. That is also completely standard. When any industry is disrupted in the initial stages, we see irrational behavior like that. We see it's the kind of resistance we expect from the incumbent industries. So again, curtailment is sort of a fundamentally irrational response to clean and nearly costless energy. But that type of irrationality is characteristic of old production systems that are poised to be disrupted by new technology that older system cannot accommodate, cannot integrate. And as a result, the old system tends to be transformed as a result. Okay, so superpower is a new way to think about something that we probably are all familiar with already, which is the overproduction from intermittent solar and wind. There's one last thing that I want to close with. And I'm happy to take questions about this because this is a little more subtle. I'm quite excited about this last piece. So when you put these two findings together, our two key findings, the thinking differently about superpower, about overproduction, which we call superpower, that's the first one, and putting that together with the clean energy U-curve. So let's put these two findings together. Okay, so at first, it may seem that it's only reasonable to focus on the least expensive 100% solar, wind, and batteries system, the least expensive combination of those technologies, which is what is represented by that sweet spot at the bottom of the U-curve. That's the lowest cost configuration, the lowest cost combination of these three technologies. And so we might say, okay, well, that's the thing to go for. That's the thing to build. Okay, but the U-curve is nonlinear, right? So what would happen if we did something different? What would happen if you were, say, California, and you decided to, instead of just going for the cheapest system, you had decided to make a 20% greater investment in solar and wind generating capacity, instead of just the cheapest? What if you said, okay, well, let's actually invest 20% more? That's a fairly modest premium, 20%. But that would move you up the U-curve. And as a result, you would get a a very disproportionate, a nonlinear, a disproportionately large return on that investment in terms of generating capacity. 20% more investment, 50 to 100% more generating capacity. Okay, but what is the consequence of that? Well, the consequence is that you would have 100 to 200% more superpower from this system, because most of the generating capacity, that additional premium of generating capacity you were purchasing with your investment, would not be covering existing demand. That's already covered. What it would be doing would be giving you more scope for producing superpower. So for a 20% premium, you could have 200% more superpower. This is a very unintuitive implication of putting these two key findings together. And so you can imagine what that would look like. What would the implications of that be for a region that chose to make that investment decision? Right, so take California, existing demand, 285 terawatt hours. Okay, here's the lowest cost scenario. It covers all of that demand, plus it generates 309 terawatt hours of superpower. So the 100% solar, wind, and batteries, the cheapest one, the one at the bottom of the U curve, produces a bit more superpower than all of existing demand. Here's how that compares to existing energy uses, right? I've converted all of the energy to terawatt hours, but of course, most of this is in terms of fossil fuels today. Transportation, residential, mostly heating, commercial, mostly heating, industrial, the industrial sector. Okay, these are how these energy uses stack up. But here is California with a 20% additional investment in superpower. So this is not non-obvious, right? This is an unintuitive implication of these of the findings that we've written about in the report. So this is, I think, worth considering with great care. If policymakers want to think about whether or not to invest in solar, wind, and batteries, they ought to think very carefully about this. Right now, the conversation is, well, maybe we should only invest to the point where we have 80% solar, wind, and batteries and leave the rest to the legacy technologies. That would not just be suboptimal, right? That would be an enormous mistake if you were thinking about disruption and imagining that that your energy system in the future would be able to take advantage of superpower.
All right, Adam, I've got to get a question in here.
Sure. No, I'm
we
finished.
lose Amory Levin, so I'm going to interrupt you again.
I can wrap up right now. That's fine. I can stop right there and take questions.
Great. And I hope Amory comes back to his camera. In 1976, I read Amory Levin's Energy Strategy, The Road Not Traveled, and it was visionary and it changed my view of the world. And I'm hoping that Amory will come back to respond to the question of whether this work is of the same level of vision and import as his work 4.5 decades ago. But somebody's moving around in his background, but we don't have him at the screen, so I might have missed my chance.
Well, I can't tell you how flattering it is to even be put in that same company. So thank you, Jim. What would people prefer? Should I leave this slide up on the screen, or should I switch to my camera? What would be more comfortable for everybody?
Why don't you leave your deck up, because I think people will have questions about various parts of it. So Amory has now come back to his screen. Are you there, Amory? You can unmute yourself. Yeah, Amory, can you unmute?
Yes, unfortunately.
So I pose the question, is this work of the same level of vision as your 1976 energy strategy, The Road Not Traveled, that got me started on my energy career 4.5 decades ago? And I posed that question to Adam, and I'm also posing it to you.
I think that's for others to say. This is of a very different character. It's useful. I posed 3 or 4 written questions about it. that I hope the group will discuss in my absence, and then I'll have to get to the recording to see what y'all said. But frankly, I don't think this is as paradigm busting. It does have some interesting features and some fairly important omissions that could make it a lot more powerful if filled in.
Did you want to pose a question? You've still got your hand up here, so.
I'm sorry, I posed 3 or 4 of them in the
Yeah.
chat, which I hope the group will discuss. And I'm sorry for that. Thanks.
Great. So Adam, I'm going to take you back to Ahmed Faruqi's question. If you had done this analysis 20 years ago, would you have gotten the same result that you're presenting today?
Yeah, that's a great question. I mean, the problem historically with applying our specific method, applying the CBET technology disruption framework, is that our approach requires an established cost trajectory for a technology. So it's without that, without an existing track record of cost improvements to extrapolate forward, you would struggle to make plausible predictions for the future costs of technologies. And from that standpoint, you could still look at scenarios, but you would be making, you would have to make assumptions and perhaps do a variety of different scenarios to compare to give a sense of what the possibility space is that you're mapping out. But our approach would have been difficult to apply several decades ago primarily because of the lack of a cost trajectory for batteries. And lithium-ion batteries really changed the game. And even still, the data for their costs are problematic. They're complicated. There are a number of factors that complicate getting a clear picture of what stationary storage is actually going to cost. And we're still in the early days of that. So certainly 2 decades ago, it would have been very difficult to apply our method to this. If anything, I think that we would not have been able to imagine that costs could improve so rapidly and consistently year after year for battery technology. I think this would have been very difficult to imagine, for example, in the 1990s. So this is all just a way of saying that battery energy storage in particular has shown quite spectacular improvement year upon year upon year. And so that would have been hard to predict. The underlying approach that we've used would have produced similar results. We would have seen what combination of solar and wind would need to go with what quantity of battery energy storage. And what really would have changed would have been where the U-curve put us in terms of the cost optimal configuration. And it's certainly, I would imagine if you were to do this in the 90s, it would have been difficult to see how we could plausibly have a 100% solar, wind, and battery system by 2030. I think that would have seemed very far-fetched at that time, given the primitive state of batteries at that point. So this is a very pleasant and spectacular surprise. And even retrospectively, it'd be difficult to know that battery technologies based on lithium in particular would be amenable to such remarkable improvemants year after year. That's the sort of thing that's
actually
extremely
posed the question
difficult
about batteries
about
5 years ago. I was presenting on a forum with Tom Stars, and I said, are we going to see the same kind of cost reductions in batteries that we've been seeing in solar? And he said yes. I'm going to queue up a few people in some order for some questions here. Fred Hewitt, then Kyle Dada, Eric Jamon, Louis Peroso, and Tim Ryan. So,
Hi, it's Fred. Can you hear me okay?
yep.
So thanks for the presentation. I was looking at the report earlier this month and quite interesting. A couple of quick observations when I put in the chat box. Experience curve analysis goes way, way, way back. The roots of it are back in the 1930s. It was refined in the 1960s by the Boston Consulting Group. You know, it's a well-established kind of thing. And in 1980, SERI, now NREL, published what I think is the first paper referring to energy technology, looking at solar thermal, actually not solar PV, but the basics still apply, when Dennis Hayes was still running SERI. So we've known about this for a long time. BNEF and other large international organizations were doing experience curve analysis a decade ago. So yes, we could have known 20 years ago what was coming, and the very recent experience at that time with the internet, telecom, cell phones, et cetera, would have pointed the way, in a fresh kind of way. So I just wanted to say that. But the second point I want to make, and I'll put a link in the chat here in a moment, is since we do understand, basic level, have a pretty good understanding of technology innovation as a basic construct in our kind of economy, why isn't that built into our planning models? This is the point Michael Grubb, UK economist, has been making for quite a long time. I put a link in for his commentary and recent paper on this. Our planning models, our integrated resource planning models, for example, for utilities, all the way up to the integrated assessment models for global climate, do not include a term for technology innovation. It's either patched in, as ex ante or ex post. And I think this is a fundamental, failure, basically, of our planning mindset. And I'm wondering if you have any thoughts on that.
Well, I have to say it's just it's a point of perpetual frustration for myself. I don't believe I'm speaking out of turn when I say that for Rethink X and Tony and the other team members as a whole that it's frustrating to see consistent errors made over and over again in different contexts. So in different industries, in different sectors of the economy, different countries. If you look at forecasts and planning, there seems to be a very large technological blind spot. And to the extent, as you suggested, that technology innovation is accounted for, it seems to be done in a very primitive and limited way. And so I guess I think there are two things to think about here. The one thing is the incentives to be accurate with technology forecasting are often not aligned well. So that's the first point, is that the incentives are a problem. And I'll bring that back to the second point as well. So that's the first thing. The second point is that technology forecasting is usually left to the industry or the sector itself that's affected. So what happens when we put those two things together? Well, take the example of energy. You have an entity like the International Energy Agency, the IEA, and it is representative of the energy sector. But if the energy sector is overwhelmingly fossil fuels, the incentives are incorrect for the industry itself to forecast its own destruction, right? Its own disruption. The incentives are not well aligned for at least a public dissemination of forecasts that flatter the competitors of the incumbent sector or industry. So this is a problem, that the incentives are not properly aligned there. And on top of that, you have the industry itself you have the assumption that the industry is best positioned to forecast the future of technologies that affect it. So naively, maybe that makes some sense, right? Okay, you're energy experts. Surely you would know what the future of energy technology holds. But and again, I reveal my own personal bias here. I think that is a very large mistake. I think that technology forecasting, technology analysis, understanding the dynamics of how technology changes, at what rate and why, that is its own distinct discipline. It's its own distinct form of analysis, research, and the expertise that emerges around that is not industry or sector specific. And so I think it's a mistake for any industry or set of disciplines to presume that it can do its own analysis, its own technology forecasting without relying on actual, for lack of a better word, external independent expertise that focuses on that. And my background as an environmental scientist, it makes this very explicitly clear. Right? So the environmental disciplines do an absolutely appalling job of understanding and accurately forecasting technological change in general. And there are a lot of reasons why there's a lot of direct antipathy to technology in the environmental disciplines. So motivations and incentives are misaligned there. But what's even more frustrating is that the disciplines don't look externally to expertise to get an accurate picture of what's on the horizon. They seem satisfied to make their own forecasts or to simply accept industry's projections of their own futures. And I think that this is a real problem. And of course, it's not limited to just the energy sector. This is a problem in general that affects all planning. And environmental policy and planning are near and dear to my heart, but I think it extends to planning of all kinds. So yeah, this is perhaps an argument. I've certainly made it as an argument for technology, the history, the present, and the future of technology theorizing and forecasting should be part of the education of our graduate students. So right now, if you get a graduate degree, a master's degree or a PhD in an environmental discipline, for example, there's no curriculum anywhere I'm aware of that requires you to understand anything about technology on a theoretical and empirical basis, nothing whatsoever. And yet it's going to be, technology very clearly is going to be one of the most important factors that drive change across the planet in the decades ahead. And if you're talking on a decadal timescale, which of course environmental analyses tend to be long time horizon analyses, technology is an important factor to think about. So on one level, it's very arrogant to believe that you can do just as good a job as somebody whose whole work is focusing on technological change yourself. Oh, I'll just do the technology forecasting myself in my model. I think that's quite poor and quite poor and undisciplined approach, given the importance of this factor in the whole equation. So yeah, as I said, you raise a question that strikes very near and dear to my heart there. So I apologize for having a bit more bias than I would otherwise have. Hopefully, I'll be more objective on these other questions.
I started this out saying I was going to shut it off at the 1 hour mark. I just didn't do that. I'm not going to do that. Adam said he could stick around for a little while, and maybe people can ask easier questions, or Adam can talk faster or something here. Get through some more of these folks here. But Kyle is co-author with Amory of at least one of his books. Those who don't know.
Adam, first of all, thank you for taking the time to talk to all of us. The advent of some of the technologies you mentioned is real, but you are making a conceptual error by using a central planning paradigm to apply them. For all the technologies, not just these three, but also supply and demand side and grid technologies, the entire utility planning paradigm changes. So you have to look at the whole system very differently, including the grid and including both sides. When you only do the central planning paradigm, which is what you've done, and utilities are doing this, you will get the same U curve, which is the overbuild curve. Doesn't have, and then you're trying to address it. Doesn't have to exist in the same way or the same magnitude. And that's a really important point. So if you take these same technologies, you also add long duration storage, you add any kind of efficiency in DR technologies, control systems, all the things on the grid you have to include, do reliability correctly, you'll find a very different mix and approach. It will still have ultimately a parabolic shape, but a very different mix of technology. So I would urge you to take the essence of what you're doing, recognize that there are other people, including large energy companies, that are doing exactly this with the full suite of technologies. And I think collectively, we're going to see a very different system emerge. So just take all these factors into consideration, and you may come up with a different conclusion as to both what's possible, but also how much it will cost, and how practical it is, you must consider the grid. And one last thing around whether the correct way to do weather analytics. You can use backcasting, but you have to look at the whole system, look forward and understand what happens when your first contingency is renewables, and plan for both stormy skies and dark doldrums and all the new set of climate effects that occur when you have a high renewable system and the covariance around that. So it's just a different planning game, but I will share with you, I work with large energy companies for most of my career and right now, the largest and more advanced utilities are working to change their entire planning paradigms to address the technology curve you showed, but many more. And it will come out much more sophisticated. And of course, Amory's right about energy efficiency. One last point, the cheapest thing you can do in this whole system is change the efficiency of the EV. That's another whole story about why we're planning for the wrong thing.
Eric, Adam, do you want to respond to that? Or
Well, I mean, I didn't hear a question. Is this? I mean, we certainly appreciate that there's that the real world complexities of translating translating disruptive new technologies into an existing incumbent system are there are enormous complexities there. And as I mentioned, for the scoping of our analysis, we make a very large number of tightly constraining assumptions. And the reason for doing so allows us to scope the analysis at a macroscopic level in order to achieve what the objective of our research, which is to answer the fundamental question: is a 100% solar batteries, so a solar, wind, and battery system possible? And is it possible? If it is possible, is it feasible economically in the limit? And what are the broad implications and choices of a system that is comprised exclusively of those three technologies? And the details of actually navigating the disruption are going to vary enormously from one region to another. And they're going to be complicated by all of the factors that I listed, right? Which I think align quite well with what Kyle pointed out. You know, the electric vehicles alone are such a wild card that it makes it very difficult to predict in a specific market or a specific region what the final system's configuration is going to look like. I will say that the largest features of the system are likely to be preserved, whatever its final structure, how the generating and storage assets are distributed, whether centrally or decentralized. The larger implications, so superpower, for example, is the one I mean. That implication holds irrespective of where and at what scale the generating and storage assets are organized. So it's important to think about what investment opportunities and what business models and what a new system, what value a new system will generate that is governed by the dynamics of very, very low marginal cost electricity as opposed to the system that we have today. So, but yes, I mean, it is the complexities in the actual realization of this disruption are formidable for sure. And we're certainly not trying to make a forecast for how those complexities resolve in any given location. We're simply mapping out the boundaries of the system so that people can sort of, so that decision makers of all kinds, investors and policymakers primarily, can cast their gaze in the right direction, which at the moment we feel is sorely lacking in most instances.
Eric.
Thanks, Jim. Thank you for your presentation, Adam. I had some feedback for you and then some questions, a mixture of both. I work with Energy Innovation, which is also somewhat of a think tank. And at Energy Innovation, I'm one of the people who thinks the most about kind of the future of electricity and electricity pricing in the context of disruption. So I'm in your camp, but I think you might be missing some things. So, you know, my first point is kind of along what Kyle's talking about, which is, you know, I looked at the numbers in your report, and before you were doing the overinvestment, you know, the super investment, you were looking at 3.1 cents per kilowatt hour average price, you know, which wholesale market folks, we call that $31 a megawatt hour. That's actually higher than some of the average prices we're seeing today, or pretty close. You know, we did a study with Lawrence Berkeley Lab and folks at Goldman School, where we showed you could get to 90% clean system by 2035 at significantly cheaper than today's system. And then we did some back of the envelope work with the LBLL folks and showed that you could, you know, push the price up a little bit more and get to 100%, especially if you introduce hydrogen pathways. And the point of this is, I think the left side of your curve might be off. I think the left side of your curve is actually pretty flat in the sense that even at 1x or 1.1x, there's pretty cheap systems that are 100% clean that are available if you broaden your parameter space outside of just wind, solar, and batteries, which is part of what Kyle was talking about. And then a question becomes, is there, you know, is there a minima, you know, maybe a shallow minima out at 2 or 3x, or not? You know, and I think there's, you know, a good mathematical question there, even in the context of the kind of technological breakthroughs that you're talking about and costs and so on. And the other question is about how does this play out? Because as things get cheaper, people start consuming the electricity, and that raises the prices back up. And so there's going to be a dynamic as you move up. You can't kind of examine how cheap things are going to get, then think, oh, I've got all this cheap power and now people are going to start using it. People are going to start using it as soon as they can start using it. My personal conviction is, even as we move down these cost trajectories, you will never really see more than 10, 15% of hours with really low prices on the price duration curve because of load side flexibility. So in some ways, I feel like you guys are being unambitious with this in thinking about how demand side elasticity will react to the technological trend. And so I don't see so much of a U-curve as a kind of slope going off to the right that might or might not have a minimum. So that's some feedback there for you. The question that I have with disruption that I would love to get your feedback on, as somebody who's thought about this area a lot, is, you know, here in California, we have this problem where we get into these contracts for solar at a certain price, and then a few years later, those contracts look really expensive. And so that's a deflationary environment. And then I keep thinking to myself, well, who wants to invest in a deflationary environment? Why would I invest in a solar farm today if it's going to be so much cheaper a year or two from now? And, you know, why would utilities, why would customers get into contracts? I'd be curious as to kind of your perspective on that. How do you see that play out in other sectors, and how that might apply here? And then the last point for you is, in all the complex modeling that I've been involved in, you know, doing production cost expansion, even with really aggressive price declines and so on, what I found is most of the modeling goes out the window, because what tells you what actually gets built is the modeler's assumption about the build rate. And most of the models end up just pegging on the build rate. And from an advocate's point of view, that's the real problem right now. We can't get the stuff built fast enough. Even if the economics is there, there's so much problem with getting interconnected and getting through the queues and so on. I think batteries will help a little bit with that, in that they allow you to leverage your transmission system a lot more. And I don't think people understand how disruptive batteries are going to be to planning in the future. But that's still a really big obstacle to kind of the speed at which this plays out, is just the inability to deploy. We just heard from MISO today that they're not going to do any ambitious planning in their 2021 transmission plan. I know this is all seems a little weeds to you, but at the end of the day, those factors will overcome a lot of the economics if they don't get resolved.
No, absolutely. So, I mean, again, I should emphasize, or re-emphasize that what happens in any given region is subject to an enormous array of different factors, right? And an important thing to emphasize is that the perspective on this disruption needs to be global, right? I mean, yes, our case studies are based on the United States. The main reason for that is that the data that are available are high quality compared to elsewhere. China, for example, very difficult to get reliable data. But this is the disruption is going to be global, and it's going to play out across a very wide range of different circumstances, and that's important to think about. I think it is easy. I think you used the word weeds. It is easy to get lost a little bit in the weeds of local circumstances, local limitations, local factors. So part of, I think, the value of what our work tends to bring with a very much a macroscopic analysis is to broaden the window of what seems possible. And I think that is in this particular case, that is a very important thing to keep in mind. I think we will begin to see in the 2020s some examples that show what is possible, but they're likely to be very local. And again, the history of disruption bears this out. It tends not to be the largest or players or centralized governments that lead disruption. We overwhelmingly see these changes begin at the edge of whatever sector or system we're talking about. And the examples that are set there show give an intimation of what is possible going forward. And leaders tend to emerge from the outside rather than from the inside. And I would look again for this disruption to outsiders and to small localities, small regions for examples of how the disruption could unfold in a way that decision makers see new value in. And this is frankly, it's quite unlikely that this is going to happen in the United States first. As much of a leader as California has been, it's probably unlikely that the business models of the future are going to appear for energy are going to appear first in any of the usual suspect locations. Typically, again, history simply doesn't bear that out. The history of disruption, we're very much more likely to see it on the edge, and so I would expect an unlikely region somewhere worldwide to do something rash, something very bold, to say, okay, well, we're going to be the ones to make this greater than 100%. Investment, this an investment plus some premium that gives us a maximal additional amount of superpower, and we're going to base a regional economic plan on that, and it's going to include very exotic decisions and plans, like we're going to give away electricity to manufacturers who move here. They're going to, instead of tax incentives or breaks or other structures, if you move your manufacturing base to our region, you're going to get free electricity from 10 a.m. to 2 p.m. or something like that. We're and that's just one example. It might be a corporation that is a leader in this and chooses to implement a radical new business model. Again, the specifics are difficult to predict, but the general patterns from history suggest that that is the sort of thing to expect from a disruption. And again, we look to the examples of how the internet emerged and how the automobile emerged and so forth to get a sense of where these new possibilities are likely to be realized first. So that's just commentary on that. As to the specific challenges that a given region, say for example California, faces, absolutely no doubt. And again, we don't pretend to have the expertise to weigh in with specific prognostications about what will happen in a local region like that.
All right, so Louis Barroso had to leave, and he posed, and a number of other people piled on a series of compensation questions. And I'm not going to pose these to Adam. He's not a pricing expert, and there's heaps of people in the Electricity Brain Trust who are. And they include, what is the compensation framework to developers to get them to develop these resources? What is the pricing framework to passive consumers for a system that consists of essentially no variable costs? What is the compensation and pricing framework for flexible load to attract some of the superpower users that Adam addressed? And what is the salvation plan, starvation plan or salvation plan for utility investors in this? And I'm actually going to propose to Amit that we schedule that whole topic of compensation framework in a low marginal cost system for a future forum here. And so that, with having said that, I'm going to pitch it to Tim Ryan next. I think I don't see other hands up. I do want to end by the top of the hour, and I'll have a question and comment at the very end. So Tim, you want to unmute yourself? You think you can find your unmute switch? You have a hard time with that, I know. Bottom left-hand corner of the screen.
Yes, I've just got 3 screens and I've got to find the cursor. Could you just slip back to the slide where you left out all the constraints you didn't consider in this? While you're doing that, I just think my questions and some of the things I was thinking about have very much been along the ones that have already been raised. And I felt a little bit that you might have been being a little bit picked on because I think right here in this slide here, you made pretty clear about some of the things that you were leaving out and said that there was, these would have a positive effect on your plan. Now, we're already in Australia at the leading edge of this. South Australia has had days where we've had net apparent demand within the state itself. And if there wasn't the interconnectors, it would have fallen over. But the issue is that most of this sort of stuff, all the driving stuff in solar has actually been in the distribution network, and as a result of that, the energy can't get back to somewhere else for your superpower type approach, which I think is quite valid. Ross Garnaut published a book 12 months ago in Australia, which his thesis was that we had to get to 7 times energy generation and then look at how we use it. But the trouble is that unlike nearly any other product, in fact, I'm not aware of another product where supply and demand must equal at the point of consumption. So every second that goes by, it's got to be equal. Otherwise, the system falls over. So without flexible demand and those things built into it, I see a lot of trouble in trying to make this work forward. And I'm just wondering how you take the broader assumptions and the data that you've had to work through from a central side model of how we actually take this out into a model that actually reflects reality of an enormous growing DER, both in the point of generation. And that's where batteries are going at the moment, which is not very cost effective. You know, the levelized cost of energy of a home battery compared to a community battery compared to a grid battery is exponential. So I'm just wondering how you think you take this work that you've done that highlights it on the data you have on a centralized model, and picking up what Kyle said about actually how we actually get this in something that's closer to reality and we see everyone benefit, and logically that's through flexible load. I think the other one that someone else mentioned in the post and I had as well is that the big thing on Ross Garno's book was hydrogen. But hydrogen, we've got to get hydrogen cost down to less than $2 a kilo for it to be viable against the alternative productions of hydrogen. Does that help?
Yeah, I mean, again, the specifics of how how a build out toward a 100% solar, wind, and battery system unfolds, and it's specifically the distribution. That's probably confusing in this context. The range of different centralized versus decentralized resources. And again, I mean, that makes it sound like it's binary. You know, as we all know, there's an enormous range of different scales that, especially solar and batteries, can be deployed at, and the costs vary non-linearly across those scales. And so, the cost, the question of cost, the question of how is investment made and who makes it. So who pays for the build out? Is private investment going to pay for this, or is public investment going to pay? What balance of the two? And the answer to these questions is that it is likely to be, there are likely to be as many different answers as there are policy domains, right? As there are regions that have to make decisions about this. So there is certainly not going to be any one size fits all answer to a question with this sort of complication. But again, I would just emphasize that the fundamental dynamics are likely to hold regardless of what the ratio to decentralized versus centralized resources is, regardless of to what extent other disruptions are simultaneously occurring alongside energy. And specifically, I'm thinking of the electrification of transportation, which has both a pull and a push effect. I mean, you were going to see a surge in demand from the electrification of transportation, but also vehicles provide at least conceivably a mechanism for additional energy storage. How that's realized in a given location is going to vary enormously. If they're individually owned, if they're fleets, if vehicle to grid is supported and rolled out quickly versus slowly, many different things to think about. But across all of that, the larger features of the disruption are still very likely to hold. And again, those are that most likely we are going to see a system that has an unintuitively large amount of generating capacity, a surprisingly small amount of battery capacity, compared to what the current narrative is. In other words, a few days, not weeks, worth of batteries being required, and that the near zero marginal cost for superpower and the scale, the quantity of superpower that is the natural function of having so much generating capacity is whether it's distributed or centralized, either way, those are going to be features of the energy system of the future, of the energy system that societies have 10, 15, 20, 25, 30 years from now. And so the real question is it possible to make good decisions today knowing that what the broad features of the energy system of the future are likely to look like. And that's the real challenge, I think, that this research that we've done poses. Can we make good decisions? Well, one good decision will be stop investing in coal power plants and natural gas power plants. You're likely to lose money if you invest in those, right? That's just a very low hanging fruit as an example. But again, who is the audience for this? Well, we need to think pretty big and pretty broad, because a lot of money gets invested and a lot of big decisions are made that could easily lock us into very large, very expensive errors, right? So Tony Siva is very fond of saying, when people ask him for his advice, the first thing he always says is, don't lose money. And there are a number of ways it's pretty obvious that you can lose money in here, right? Spending $50 billion on nuclear power plants is a great way to lose money, right? Continuing to build coal or natural gas power plants, probably a very good way to lose money on a 10 to 20 year time horizon. So I'm being a little flippant here, and I don't mean to evade the complexity issue of all of the details in any given locality. But again, I want to emphasize where the value, where the usefulness is in the kind of research that we publish. And the usefulness is very much at the macroscopic level for understanding disruption. One more thing to say, one final thing to say about that is that the history of disruption shows us that the new systems that emerge are just radically different. They're completely different. They have completely different behaviors and architectures and constraints and metrics and sources of value than the systems that they replace. And so it is a matter of intellectual and other planning discipline, decision-making discipline. It's very important to avoid assuming that current technology is just going to be subject to a one-to-one proportional replacement by new technology. We're going to replace an old coal plant with a solar plant, maybe with a battery attached to it, basically performs the same way. And that the existing system and its behavior is unaltered. And if that's your assumption, then questions like, well, how are we going to get all this new solar into this? How is this old system going to incorporate these new technologies? That tends to be a mistake. When the telecom companies were asking themselves, how are we going to build all this new bandwidth capacity, and who's going to pay for it, and how are we going to make any money at this, and how are we going to keep charging for phone calls once everybody's online, and how are we going to keep selling individual books and individual DVDs and individual music albums? All of that was a mistake, right? And the caution that research like what we put out, the cautionary tale is to look to the history of disruption and expect something very similar for energy. And again, so that's I think that's the big picture. And then of course there's always one more thing. The one last thing to think about is the time horizon, right? This is not 2050 or even 2040. All of this is the next 15 years, not the next 30 to 50 years. When the transformation to a new system, the time horizon for transformation to a new system is likely to unfold very, very much more rapidly than seems intuitively possible at the outset. And again, that's just disruption 101. It happens every time. Oops.
Jim, you're not muted.
Sorry about that. I've been so good about trying to stay muted. Adam, thank you very much for giving us this time and this opportunity for discussion. Now, I've got probably 100 questions, most of which wouldn't be directed at Adam. I mean, top of my list and on several of the comments were, what's the transmission and distribution compensation framework and market structure that works for this? how the paper talks about Walmart giving customers free EV charging power as an enticement to park at their store long enough to charge. And we've actually seen that at a number of retailers with level 2 charging. If you get a customer with a fancy new car in your store for an hour, the electricity that you and charging service that you donate to get them there is a small customer acquisition price. What happened is a bigger grid, more national interconnection, sort of the DC grid dream, a relevant part of this to diversify the production of renewable resources across the country rather than locally. And the small amount of storage that the paper identifies suggests that maybe that too is going to be obsolete. Anyway, I've got questions, but this meeting and this electricity brain trust are an example of disruption. In the early part of my career, in 2 months to put together a mailing list of 400 or so energy experts from around the world and actually get 600 messages communicated between them wouldn't have been possible. Calling a meeting like this on 1 week's notice and bringing people together from Australia, from the US, from the UK, and Zusa is in, I think, Hungary, would not have been possible. Probably there's a number of us on this meeting who were not using telepresence much before the COVID crisis. And I expect that the COVID crisis, while it's levying a very heavy cost around the world, is also creating a collateral benefit that in the acceleration of telepresence and reduction of travel time and travel stress that is a further disruption. So this whole meeting is an example of disruption, and I thank you, Adam, and thank Tony for us. And I'm gonna try and save this recording and save the chat and then end the forum here.
Thanks, Jim. Thanks,
We'll
Adam.
have another one.
I was just saying,
Thank you,
thanks,
everybody.
guys.
I think this is a very good step forward and a good process. Thank you.